Hey guys, so in this video we're looking at kind of an introduction to radicals and radical notation, and then mostly focusing on rational exponents, which turn out to be another way to write radicals. So let me start off with the radical piece. So given this radical expression, so we have this little square root looking thing with a funky little n and an x. The funky little n is called the index. When there's nothing there, it's an invisible 2, so it's a square root. If it's a 3, it's a cube root. 4, it's a fourth root, etc. And anyhow, that little number up there is called the index. X is the radicand. That's the stuff underneath the radical. And then this is the radical sign. I often just call it the radical. But that's just a little bit of terminology that goes with this. There's this list of perfect squares, cubes, fourths, fifths. If you're in my class, my students over the years have talked me into giving them this for the test. So if you're in mine, Derek Madison, then you'll have this for the test. If you're in someone else's, you should ask your instructor about that. But these are going to be handy in this section to an extent, and then even more so when we get to 8.2, the next section, we're simplifying radicals. This turns out to be a pretty handy little sheet of numbers right here. And so let me just kind of introduce the radical notation, and we'll head into the rational exponents from there. So square root 4, probably you know it's 2. So what does square root 4 actually mean? Square root 4 is asking, one way of saying is what times what makes 4. Another way of saying it is if we had a square of area 4, how long is the side? Because what times what, that side times that side makes that area of 4. And so if the area of the square is 4, the side would be length 2. You can see if I had an area of 9, and then the side would be length 3. So perfect squares are literally squares with like sides that are, integer lengths. So 1, 2, 3, 4, 5, 6, and then you square it, and that gets you the area of the square. So when we're taking a square root, we're finding quite literally the length of the side of a square of that area. So square root 4 is 2. Now that we've worked that out. The negative of square root 4, so the negative is happening after the root. So it's just square root 4 is 2, and then, it's negative. And then this one, this is saying what times what makes negative 4. And there is no number times itself that makes negative 4. By the time we get to the end of this chapter, we're going to have something else to say about this, but for right now, it's going to be a D and E. Don't love that. It should be no real number because it turns out there's imaginary numbers. But for the computer, it's going to be a D and E. Cube root. So what a cube root is basically if you had a cube. Let's see if I can draw a cube. Could have done this ahead of time. Okay, so there we go. So if I had a cube and it was 8 units, the volume was 8 units, so 1, 2, 3, 4, and then 5, 6, 7, 8 on the back, where you can see kind of a layer of 4, another layer of 4. Then the volume of this thing would be 8, and volume is a 3D measure, length times width times height. So the volume of the cube would be 8, and then the side again would be 2. So when we're finding a cube root, we're finding the length of the side of a cube of one of these perfect sides. So if 1 cubed would be 1, 2 cubed makes 8, 3 cubed makes 27. And we've seen these numbers when we did factoring, so they probably look a bit familiar. Likewise, the same with the squares. Hopefully those are a little bit familiar to you. So cube root of 8 would make 2. And when we were doing the factoring, we just couldn't say that that's what we were doing because we didn't have that notation yet, but we kept breaking down the 8, making it a 2. We were taking the cube root. This is very similar, so this is just the negative of cube root 8. So we're saying cube root 8 is 2 and then make it negative. But now this one, if we think about negative 2 times negative 2, I guess parentheses would be better, times negative 2, that really does make negative 8. So under cube roots, we can have negative values because we have 3 numbers and that gets us an extra negative sign. But we can't do it under a square root or, for that matter, any even root. So if this is a 4th root, I couldn't do it. 6th root, 8th root, no good. But odd roots, we can have negatives. So this would just be negative 2, but for a different reason than here. This one is like negative 1 times the cube root of 8. So we do our cube root 8 made 2 and then multiply by the negative after the fact. This one, that negative's on the inside. So what I just said here was even roots, a negative under the radical does not produce a real solution. D and E for the computer. Odd roots just do what they would do. If you have a negative, 3 negatives do make a negative, so it's all good. and likewise fifth roots and seventh roots. And then up next we have a little bit of simplifying radicals, and we're going to do a bunch more with this in the next section. So these ones are all going to work out really nice. In the next section we'll kind of see how to deal with them when they don't turn out quite so nice. So square root 36, and so that would just be our 6, and we kind of saw that back when we were doing factoring. So when we see a 36, what times what makes 36? 6. So that's going to come out as 6. The way I do the exponents, I really like. Basically for every pair, because what this 36 is doing, let me just kind of scratch work it up here. If I have square root 36, I have the square root of 6 squared. And what's happening is that root undoes the square, and what I'm left with is that 6. And so basically for every pair of 6's, because I could also think of this 36 as square root 6 times 6, so for every pair of 6's, 1 comes out of the radical, because that square undoes, or that root undoes that square. And so if you think about how many pairs of x's you have here, like saying it that way, it makes it hard, because you're counting, like, trying to count pairs up to 12. So I think, okay, there's 6 pairs. But the easy way to do it, so for every pair, 1 comes out. So like here, there's an invisible 2, so 2 goes into 2 once, so 1, 6 comes out. Here, 2 goes into 12 on that x 6 times, so 6 x's come out, and that's all there is to it, because all we're doing is for every pair, and we got 6 pairs, 1 comes out. So 2 goes into 8 4 times, so y to the 4th comes out. And it's such a nice, easy way to think about it. And then the other cool thing is that generalizes to when it's a cube root or a 4th root. By the way, in the computer, never ever type that 2. I like to write it there just to kind of show what I'm doing, but don't ever type the 2. Square root should just be a nothing there. For a cube root, we can generalize this to the same thing. Now it's for every group of 3, 1 comes out. Because, like, for instance, this 8 is really the cube root of 2 cubed. So we're saying 2 goes into 3 once, so 1, 2 comes out. And then for the x's, 3 goes into 33 11 times, so 11 x's come out, because there's 11 groups of 3. 1 comes out for every group of 3. And 3 goes into 15 5 times, and that's it. So pretty cool. Over here, 81, and this is where the sheet can kind of be handy. So if we're looking at a 4th root, we come to our perfect 4ths column and go 81. Oh, okay, 3 times 3 times 3 times 3. I think I said the right number, but if I didn't, I meant to say it 4 times. So this is 3 to the 4th. I'm going the 4th root of 3 to the 4th. So the 4th root undoes the 4, and I get a 3 out front. 4 goes into 16 4 times, so 4 x's come out. 4 goes into 4 once. So y, probably don't want to do y to the 1st, because we usually don't write the 1, but it's like y to the 1st. So that's a really easy way to look at the exponents, and we'll do more with that in the next section. Okay, and then this next round of problems is the ones I would have you guys try in a lecture class. So square root negative 25 is a DNE, and so I'll go through them a little bit faster because they're similar to the ones I just did. So we got a 4th root of 81 again, so but this time with the negative in front. And so if the negative is in front, that one's okay. And 81, remember, was 3 to the 4th. So the 4th root of 81 is 3, and in this case negative because of the negative in front of the radical. This time we got a negative inside, but it's okay because it's a cube. And if we don't know our 2/16, that's where it's handy to grab the sheet and go, 2/16 is 6 cubed. So this would be the cube root of negative 6 cubed. Cube root undoes cube, and we just get our negative 6. Here, square root of 49 is 7, so 7 is going to come out. If it helps to think of that little 2 there, you might as well do so. So 2 goes into 6 3 times. 2 goes into 10 5 times. And that's just, I got 3 pairs, so 3 come out. I got 5 pair here, so 1 comes out for every pair. And now cube roots, same idea, but now we're just groups of 3. So cube root of 27, remember 27 is 3 times 3 times 3. So cube root 27 is going to bring out a 3. 3 goes into 3 once, so I just get an x out, and 3 goes into 12 4 times. so y to the 4th. And then number 11, 4th root of 16, got to be 2, right? Because that's the only thing small enough. And then 4 goes into 8 twice, and 4 goes into 25 times. Okay, and then here we get fractional exponents. And fractional exponents are another way of writing roots, is sort of the deal. So if I have x to the 1/2, that's the same thing as square root x. And in general, I'll write this a little bit bigger right here in case that's not showing up so well. X to the 1 over n is the nth root of x. And so if this is 1/2, then it's like to the 2, so it's their square root. If we have x to the 1/3, it's like the cube root, and so forth. And then over here we have x to the m over n, and that one, you can think of it as this 1 over n to the m here, but I like thinking of it as x to the power over root. So if I see x with like a fraction, I think power up top and then root down below for the exponent. And I think that using the words is going to be better than sort of the symbolic for that one. And then here I just have our rules for exponents because we're going to need them as we go a little further into the section. And these were introduced either back in section 0.4 if it's 098 or the chapter 4, 4.1, 4.2 if you came up through 094. So right here I got 49 to the 1/2. So 49 to the 1/2, that means the same thing as square root 49. I don't have to write that out, but I can. And I can just really, 49 to the 1/2 is just 7, but just to show these are the same thing. Here, and this is one where we kind of have to think about which one is it. So this is like -1 times 49 to the 1/2. So this is the one where you get a legit answer. This would be the equivalent of the negative of 49. This one where there's the parentheses, this one's the equivalent of that one with the negative on the inside. So that one's our D and E. And then this one is our -7. Down here we get 8 to the 2/3. So let me write it a little bit bigger so you can see. So 8 to the 2/3. I always want to do the root before the power because the power is going to make it big, and I would much rather make it smaller before I make it bigger. So I'm going to think of this as 8 to the 1/3 squared. And that 1/3, remember, is like a root, so that's a cube root. So this is the same thing as cube root 8 squared. And you don't have to write all these steps. This is just me kind of showing how this 2/3 relates to something that's maybe easier to think about. And then cube root 8 makes 2, and then still squared would make 4. And so if you just think power root, so cube root 8 and then squared. And so you can really just go from here, cube root 8 is 2, squared makes 4, and skip all that stuff I did in between. But I think it's helpful to see it written out, at least for the first time. For number 16, we got 1 over 25 to the 1/2. And remember, when you have that negative exponent, that has to come downstairs and to be rewritten as a positive exponent, otherwise it's not considered simplified. That is the same thing as square root 25, which that just means it's 1/5. And then this one here, this one has this property, property 5, that kind of pretty much no one knows. And it just says if you have a fraction to a negative exponent, rather than doing some kind of crazy 1 over that, which is actually kind of a pain in the butt, you can just flip the fraction and then change the sign. Because all that stuff that you'll do if you do the 1 over, when you bring it up and flip it and do all that, it's going to end up the same thing as if you just flip it over and change the sign. So I'm going to think of this as 9/4 raised to the 3/2. And so 3/2 is the same thing as the square root of 9/4 because it's the 2's downstairs, so that's our root. And then that's going to be cubed. So square root of 9/4 would be 3/2, and then cubed would be 27/8. Okay, these next 5 I would have you guys try. So 16 to the 1/4 is the same thing as 4th root 16, so that would make 2. Negative 27 to the 1/3, that's the -1 times 27 to the 1/3 one. Wouldn't matter, it comes out -3 either way, but if we were trying to write this in root notation, we don't have to, we just have to jump to the answer. But it would be that one, not the one with the negative inside, and that comes out -3. This one would be the kind with the -125 on the inside. Pretend like that looks like a negative. And so this would still be -5, and it's okay because it's a cube root. Here we got that negative exponent, and that's a 1/2. So we'll rewrite this as 25/16, and then to the positive 1/2, which is the same thing as a square root. So square root 25 would be 5, and square root 16 would be 4. And then this one is, let me write that a little bit bigger. So 8/27, and that's to the 4/3. So that means we have a cube root and then to the 4th. So I don't want to do to the 4th first because I don't want to know what 27 to the 4th is, because that's a big number. But if I do my cube root first, it's a lot easier. So I'll do cube root of 8/27. And then once I get that, I'll raise that to the 4th. So cube root of 8 makes a 2, cube root of 27 makes a 3, and now to raise that to the 4th isn't such a big deal. So 2 to the 4th would be 16, and 3 to the 4th would be 81. Okay, and then in this last part we're doing properties of exponents and fractional exponents. So very much like what we did back in 94 or earlier in the course, it's with fractions instead of whole numbers. So this first one, we have 2 exponents that are multiplying, and so I'll just remind you that that's property 1, where when they multiply we add the exponents. And so that's going to look like x to the 2/3 plus 1/4. And so then to add those I have to do a common denominator. So 3s and 4s, so best I can do is 12. So I'll do a 4/4 right there. And right here I'll do 3/3. So that gives me x to the 8/12 plus 3/12, or that equals x to the 11/12. And while we type the exponents kind of squished on the side, I think it's much easier to do operations with them. When you rewrite them, write them over and under like I am. It's easier to see where the numerator and denominators are. This next one's a pretty good example of that. So when we're raising something to a power, we're multiplying. And so that's property 2. And I'm going to take a second and rewrite this just to make it clearer. So y to the 10/3, z to the 1/2. And then that's all to the 2/5. And I think if I write it that way, it's much easier to see what's going with what in terms of all those numerators and denominators. So I think I'm just going to multiply them out, and then I'll reduce as a second step. So for now, I'll just do the multiply. You could reduce as you go on a couple of these, but I'll just do it afterwards. So this is going to be 4 times 2 is 8, 3 times 5 is 15. Y, so 10 times 2 is 20, 3 times 5 will be 15, and z to the 1 times 2 is 2, 2 times 5 is 10. And now reducing my exponents, I get x to the 8/15, and then this will be 5 goes in 4 times, 5 goes in 3 times, so y to the 4/3, and then 2/10 is the same thing as 1/5. And so, like I said, when I'm actually doing math with them, when I reduce, then I don't mind writing them sideways, but I think it's easier if you kind of write them the way your brain's used to seeing them. Number 25, so this is where we have division. And so remember, for division, that is property 3 here, where we subtract the exponents. So this one will look like x to the 2/3 minus 8/3, and then y to the 4/3 minus 1/2. So this already has a common denominator, but this doesn't. So this is 3/3, and this is 2/2. So 2 minus 8 gets me negative 6/3. And then y to the, this would be 8/6 minus 3/6. So this is x to the negative 2 when I simplify, and this is y to the 5/6. And then the only other thing that we have to remember there is when we have these negative exponents, that's property 4, and we have to write, if we get a negative upstairs, we have to write it in the denominator. If we get a negative in the denominator, we have to write it in the numerator. And that changes it to positive exponent. So this x squared really belongs downstairs, so our answer should be y to the 5/6 and then over x squared. And then number 26, we're going to run the 20 in. If it helps to think of it, actually let me rewrite it a little bit bigger so you can see it on a smaller screen. So y to the 1/5. And then I'm going to think of that 20 as 20/1. And so just to show the canceling that's about to happen, this would be x to the negative 20/2. I'm going 1 times 20, 2 times 1. And then remember, it belongs to the denominators also. So this is going to be 20 times 1, and then 5 times 1. And then just kind of cleaning that up, I get x to the 2 goes into 20 10 times, so x to the negative 10. And then right here I can reduce and get y to the 4. And then because that's x to the negative 10, I got to go that last step, and it becomes, when there's nothing left upstairs, we just do a 1 placeholder, and then x to the 10th and y to the 4th. Okay, and these are the three I would have you guys try. So for this one, we'd have x to the 4/3, and there'll be plus 1/2. And so then we're going to go, we need a common denominator because we're adding. So 2/2 right there, and 3/3 right here. So x to the 8/6 plus 3/6. So 8 and 3 makes 11/6, and that would be it. These two are dividing, so that's going to be a subtract. So that's going to look like x to the 2/5 minus 2/3. And then I can go 3/3 right here, and 5/5 right there. So that will equal x, 3 times 2 would be 6/15 minus 10/15. So that's going to make x to the negative 4/15, but we can't leave the negative exponent. So final on that's 1 over x to the 4/15. And then this last one's a little bit of a commitment. So first thing I'll do is run that 4 through. And that's going to go 4 times that 5, so that's going to be x to the 20/2, y to the negative 8. And then this is going to be 2/3 downstairs, and y to the 1/2. So that's still kind of a mess. I could reduce this and make it a 10, which is good. And I could bring that y downstairs, I guess, because right now it's negative, so I could do both those things. I could also just do this as I think I'll just do it as a subtraction. So let me do x to the 10, y negative 8, and then x to the 2/3, y 1/2. So now I have to subtract these exponents. So that's going to look like x to the 10/1 minus 2/3. And then we'll have y to the negative, let's say 8/1, and then minus 1/2. So then I can do, right here I'll do a 3/3. That gets me common denominator there. And then this would need a 2/2. So that's going to be 30 thirds minus 2 thirds, and y to the negative 16 halves minus 1 half. I think I'll go this way with it. And so 30 minus 2 would be 28, so x to the 28 thirds. And then this will be y to the negative 16 minus 1 would be minus 17 halves. And then I just need to write this with a positive exponent. So that will be x to the 28 over 3, and then y to the 17 halves. So that one's pretty messy, but that wraps up the section.